For part A, we will start with finding the reduced mass, which is equal to the product of the two masses over the sum of the two masses. And using the given masses, we have 1.993 times 10 to the negative 26 kilogram times 2.656 times 10 to the negative 26 kilograms over the sum of those two. M1 plus the value for 2, and that will give us a reduced mass of 1.139 times 10 to the negative 26 kilograms. And we'll use the reduced mass to find the moment of inertia for the system. Which is m sub r times r squared, so 1.139 times 10 to the negative 26 kilograms times r, which is given as 0.1128 times 10 to the minus 9 meters quantity squared. This will give us a moment of inertia of 1.449 times 10 to the negative 46 kilograms. And now we can say that the energy rotational levels, or the rotational levels, are given by L times L plus 1 times h bar squared over 2I. And I'm going to put the h bar squared over 2I in the front when I plug in the values. 1.055 times 10 to the minus 34 joules second quantity squared over 2 times I, which we just found as 1.449, 10 to the negative 46 kilogram meter squared. I forgot the meter squared up front. So this will give us times L plus 1, and this will give us 3.838 times 10 to the minus 23 joules times the quantity L plus 1, which is the same as 0.2395 milli-electron volts times the quantity L times L plus 1. So now if we know the values for L, we can find the rotational levels. So for this problem part, we have L equals 0, 1, and 2, which means E sub 0. That means plugging in 0 in for L in here will give us 0 times the 0.2395, which is still 0. E times E sub 1 would be what we get if we plug 1 in for L, so that would be 0.2395 milli-electron volts times 2 times 2, 2 times 1. 1 plus 1 is 2 times 1 is 1. And that will give us a energy rotational level of 0.479 milli-electron volts. And lastly, for E2, we get the 0.2395 milli-electron volt times 2 times 3, which will give us an energy of 1.437 milli-electron volt. And for part B, we can say that the energy, photon, and wavelengths are given by the energy photon will have the difference between the two energy levels, which would be E2, which is 1.437 milli-electron volt, minus E1, which is 0.479 milli-electron volt, or 0.958 milli-electron volt. And that means that lambda, which equals hc over E, would equal 4.136 times 10 to the minus 15 EVS times the speed of light, 3.0 10 to the 8th meters per second, over the energy difference of 0.958 times 10 to the negative 3 EV, and that gives us 1.29 times 10 to the negative 3rd meters, or 1.29 millimeters. For part C, we need to use the selection rules for the vibrational and rotational transitions of a diatomic molecule. And since a photon is emitted as the vibrational energy changes, the selection rule of delta n equals -1 will tell us that the n has to decrease by 1 in both of the parts that we have in part C. And we're told that in part A of this problem, the initial value of L is 0, and the final value of L is 1. And for part B, it's the other way around. L initial is 1, and L final is 0. And then the difference between the 1 and the 0 levels, as we saw before, if we take E1 minus E0, that will give us, if you look at part A, that will give us a change of 0.479 milli-electron volts, which is the same as, excuse me, 0.000479 electron volts. The vibrational energy level separation for Cu is given by H prime omega, and if we plug those in, we find that this value is 0.2690 electron volts. So now to find the wavelength of the photon emitted for part A of part C, I know that sounds weird, the change in energy, or the wavelength, is going to be hc over the change in energy, or the energy difference between the level and the vibrational energy. So this will be 4.136 times 10 to the negative 15 electron volts seconds times the speed of light, 3 times 10 to the 8th meters per microsecond over the energy in this case is going to be 0.2690 electron volts minus the 0.000479 electron volts. And if we do that, we get a wavelength of 4.618 times 10 to the minus 6 meters, or 4.618 micrometer. And for part B, now instead of this h bar omega being a excuse me, a loss, it will be instead of it being a gain, it will be a loss of this amount for the carbon monoxide molecule, and the energy difference will also be a loss because it's going to be emitted. So lambda would equal, in this case, hc over E, and we know this value is 4.130 times 10 to the 15th negative electron volt seconds times the speed of light, which is 3.00 10 to the 8th meters per 0. And the energy now, because both of these energies are lost, it's going to be the sum of the two energies instead of the difference, and that will give us a wavelength of 4.601 times 10 to the minus 6 meters, or 4.601 micrometer.